Alright, this activity should be similar to the last one, except we're using two heaters now. We're going to derive a physics-based model now of two heaters, and we're going to compare that output to what the actual output we measure is with the temperature control lab. Two distinctions between the one heater model and the two heater model. The first is that we will have both convection and conduction occurring between the two heaters. The second is that heater 2 has a maximum output of 75% of 1 watt. So its alpha value will be a little bit different. The alpha value before converted a percentage to 1 watt, so it was actually 1/100th since it maximum 100%, 1 watt was being put into the system. Here it's going to be 0.0075. That way 100% is equal to 0.75 of a watt. I had to do the math in my head. And I don't know why, we could just scroll down. So here we go. 2 heat transistors, 2 sensors, and 1 LED is our system. We have our initial temperature and ambient temperature. We have initial temperatures for both heater 1 and heater 2. And this factor is here's what I was talking about. So the alpha value is 0.0062. I lied, I apologize for that. And then heater 1 output is going to be 1 to 100. There we go right here. Heater 1 factor is 0.0123 watts per percentage heater. Surface area between the heaters is going to be is going to be 10 centimeters. And the surface area between them, where they can convect and radiate energy between them, is going to be 2 square centimeters. So let's look at how we have this now. Not only do we have the Q coming into the system from the heaters, but for each system we have Q coming from convection and conduction. And I have Q1, 2 because whatever heat goes from one and goes to the other will be, these values will mirror each other. Any heat that's leaving 1 to 2, 2 is going to receive, and vice versa. So we just need to make sure that our signs always are consistent. So one way to do that is to have consistency and just have that one quantity we use for both. So QC12 I've defined as the lumped sum parameter for heat conduction and convection times the AS, which is the area between the two, times T2 minus T1. And then similarly, the radiation between the two is a Stefan-Boltzmann constant times emissivity times the area between the two, and then times the difference to the raised to the fourth of T2 minus T1. But you'll notice we always are T2 minus T1. And so because of that, the Q is going to be positive for the first one and negative for the second one, as far as the two values right here, the two values in between, showing the heat transferred between the two. Just as before, we still have mass times heat capacity is equal to the transient term. That's the same for both. We also have radiation. It's the same for both, except we're just changing which heater is which, or which temperature is which, I should say. We have radiation, we have heat conduction between the two, and then finally we have the alpha value, how much heat is coming in due to the heater. So we'll go ahead, we'll now start simulating our physics-based model, just like we did before. So again, we're going to clear all, close all, and CLC. We'll set 10 minutes of time points. We'll set our heater values as an array, 2 arrays this time, and then our heater steps. So at 6 seconds, we'll turn on heater 1. That will be at 7 seconds. Let's change that to 6. And then at 300 seconds, let's change that as well. Sorry, I was typing on the wrong keyboard. And at 300 seconds, we'll turn on heater 2. Both of them will turn on to 100. We assume an initial temperature of 23 degrees Celsius. And then we store our time right here. Similar to before, this time we have heat 2 as a function. And if we scroll all the way to the bottom, we have heat 2. We take our parameters that we discussed before. This time we unpack 2 from x. If you remember how this is situated, x is all the variables that are being integrated. So we have to store them in that array and then unpack them. We calculate convection and radiation, and then we calculate our differentials and pack them in a vector. Sometimes you can do a semicolon here, or you can do this apostrophe here to make that a vector. Either way, we want a vertical vector, a column vector, however you want to call it. We just need it straight up and down due to MATLAB conventions. Finally, we do a plot of the results. So let's go ahead, we'll run this section and see what our results are. So we can see at time equals 6 seconds, heater 1 turns on, and we'll notice that heater 2 is creeping upward as it receives some heat from heater 1. And then once it turns on, it ramps upward in a similar fashion. So we'll go ahead, we'll look at the temperature control lab code. Shouldn't be too much different. We're going to clear all, close all. And we will, it's actually not clear all, close all. I'm not sure why we're doing that. Instead, we want to be able to compare the two, so we want them on top of each other. We're going to simulate for 10 minutes, which is going to be 600 loops. And we're going to create time, T1, T2, predicted T1 and 2 at each one of those points. The error and power allocation are going to be stored in error 1, error 2, as well as the Q, which is then going to be, Q is a two-dimensional array here, and we're going to step up 10 seconds until the end, and then the first, so we go row then column, so in the first column, we'll set it to 90, and then at 300 seconds, we'll set the second one to 80. We're going to start the clock, and we'll set previous time, and then this will help us animating it all, and we should predict the, you can see, here's the Q's down on the bottom subplot, and we have the predicted and experienced values up top. So then you can see here we have our loop of what's going on. We have II for 1 to loops, and so II here is tracking the iteration number. And then we'll set the heater values, we'll assign the heater values. We'll plug them into the lab function so they're implemented. Here we're doing a timing algorithm. Here we're going to pause and we're going to estimate the difference in time. We'll then record the change in time using this function right here. And then we'll perform our nonlinear energy balance to record our predicted temperatures. And then we'll read the temperatures for the actual ones. We'll also record the error, and then we'll plot all of these. And finally, one of my favorite things, personally, is that we'll save all of these. And the nice thing about saving them is, let's say something goes wrong when we're plotting, or we want to look back and use this data. We have it saved, so rather than wait 10, 15 minutes for our data to run again, we're able to just run it. And finally, we write it to a CSV. There's also videos showing you how to do this in Simulink, or at least how to implement the control in Simulink. And I'll let you just follow the link we have for that with the Simulink values, with the Simulink files. There we go. So let's go ahead. We're going to run this now. So just watching it as it goes through. That would be why we cleared all, closed all. Let's just do that. Open a command that'll clear lab. And then we're going to return and put in that clear all, close all CLC. And we'll run it again. Connecting to lab, looks like there's no problem. There we go. So we already have some error, mainly because the heater values are higher than they were originally anticipated to be. So that's that blue line we see going up. So the energy balance error is normalized. That's how we're able to do that. Or sorry, if you look on this bottom graph, cumulative error is on the left with a different axis than power level, which is on the right. So we'll go ahead. I will pause it for now, let the test run, and then we'll discuss the results afterward. All right, and we're finished. Let's look at this. We could tell right off the bat that we were going to be higher in our gain for our first heater. We noticed that similar to as we predicted, heater 2 did go up, but because heater 1 was much hotter, heater 2 as well radiated more heat. As we go on, heater 2 turns on. We see something similar. It's a little bit hotter than anticipated, but it does follow a similar trajectory, although it's a little bit smoother as there's that dead time that happens that our physical model doesn't anticipate. And then it started at a higher temperature, it has a higher gain most likely, and so it's also going to increase to a higher temperature. So look at the next one at how we optimize our models and fit them to realistic data. So we'll see you then.